Stripping down science. The Naked Scientists.
What is the cure for caffeine addiction? And how would you know if you had it? And I'm not sure I really want a cure for caffeine addiction.
Does having high testosterone mean more female offspring?
And do parallel universes exist? And if they do, how could we find them?
The answers to all of those questions are on the way, plus news of a very lonely planet that astronomers have spotted all on its own deep within interstellar space. Plus, we'll be attempting the Twitter equivalent of a Mexican wave around the world. Find out how you can join in just a second.
The Naked Scientists podcast is powered by UK Fast, the UK's best hosting provider. On the web at ukfast.co.uk.
Hello, it is Sunday the 18th of November. This is The Naked Scientist with me, Chris Smith, and also with Dominic Ford and with Ginny Smith. Ginny, an email for you from Randy. He says, what pigments are involved in making hair blonde or red?
Well, the keratin that makes up the structure of your hair is actually white, so it's all about these two different types of melanin, which are the pigment that gives your hair colour. So there's eumelanin, which can be black or brown, and there's pheomelanin, which is a sort of reddish-yellowish colour. And it's the proportions of each of those that make your hair a different colour. So if you've got brown hair, you've got lots of eumelanin and not as much pheomelanin. Blondes will have any real proportion of the two, but not very much of either of them. And redheads have a lot more of the pheomelanin and not so much of the eumelanin.
And peroxide blondes?
Well, not sure what they would have had originally.
Lots of eumelanin, presumably,
Probably,
if they needed to
if they
diet.
need the peroxide.
Catherine's on the phone. Hello, Catherine.
Hello.
Where are you?
Hemel Hempstead in Hertfordshire.
And what can we do for you?
I just wonder, is there any scientific evidence for parallel universes?
Dominic, what do you think?
Well, that's a rather interesting one, because there's certainly a lot of scientific talk about parallel universes, but they're impossible to observe because by definition everything we see around us is in our universe. The reason why theorists sometimes talk about them is because you can make neater, simpler theoretical models of the universe we have if those models also predict the existence of other universes that maybe have different laws of physics. For example, our universe has complexity in it as a result of galaxies and stars collapsing as a balance between gravity and gas pressure. And that means those two forces have to be in a very fine balance. If they weren't in fine balance, we wouldn't have complexity in our universe. We wouldn't be there. So why is that balance there? Well, perhaps it's because there are other universes that have much simpler and less interesting laws of physics.
So there are lots and lots of different universes where the rules or the parameters may be slightly different, and we're here just because we happen to be in the one for which that physics works for us.
That's a very controversial idea, but that would certainly be what Martin Rees, for example, Astronomer Royal, would say.
So, Catherine, Dominic has explained that we may just be one of many. I guess you'd also quite like to know whether or not we can detect them if they are there.
Yes, definitely, yes.
That's really quite difficult because all of the light that we see is travelling through our universe. There have been some bits of theory that have predicted that perhaps there could be interactions between parallel universes, objects like white holes and wormholes. The problem is those are really speculation at the moment. So I don't think there's any imminent prospect of us getting any evidence for them.
Michio Kaku's got quite a good book called Parallel Universes, and in there he talks about the fact that because we believe gravity should be able to propagate between these different universes, if they exist, that detecting the gravity waves coming from one into the other may be actually the way to infer their existence. And there are various experiments that scientists are doing to look for gravity waves, aren't there?
That's right. There are several experiments looking for gravity waves, and I think it is likely we will detect them in the next 5 to 10 years. And that will be very exciting because we have many competing theories of gravity, all extending Einstein's general theory of relativity. And it will be gravitational waves that will really distinguish between those and tell us what we're looking for.
Dominic, thank you very much. Now, earlier this week, the BBC celebrated 90 years since the first ever broadcast. And for the first time in its history, all of the radio stations and networks that make up the BBC, nationally and internationally, got together to broadcast one specially commissioned piece of content for the time. And we thought that, given the importance of this occasion, we would do our own version of this. And, of course, broadcasting has come a very long way in the last 90 years or so. And it's now really breaking down those traditional barriers of what we regarded as local versus national or even international. And the rise of social media is totally changing the landscape, and the ability to reach out from one tiny corner of the world and influence people all over the world has never been more important. And so what we thought we'd do is attempt a naked Twitter Mexican wave on the programme this evening. And in our ops room, and about to press the button, and with us now is Ben Valsler. So what we're asking people to do is to look out for our Naked Scientist tweet, which Ben is going to tell us what it is in just a second. We are going to fire this off now, and over the intervening 55 minutes we have left of this programme, give or take, we are going to attempt to get to as many countries as possible. We want you at home to help, and we want to start here in Britain, so we need lots of people in Cambridge to start this off, and we want to take Cambridge to the world. Ben?
I am about to tweet Cambridge to the world to Cambridge with love. So here we go, and let's see quite how far around the globe we can get in our remaining 55 minutes. 3, 2, 1... It's tweeted. So that tweet has been posted. We're now going to see who replies to that, to add their location, to say where they are, and we'll see if we can get a wave going around the world to prove that this sort of technology and the internet really can bring the entire world together.
So if you tweet back to us at Naked Scientists, we will then retweet your tweet back to us saying hello wherever you are, back to all of the thousands of people who are following The Naked Scientists on Twitter, at Naked Scientists, and with luck you'll be able to see your tweet going around the world. We'll be rejoining Ben shortly to find out how it's getting on. Randy's on the phone. Hello, Randy.
Hello, Chris. Physicists talk about dark matter being in our universe, which is difficult to detect. If gravity waves can propagate from alternate universes, could that be a manifestation of those gravity waves that we're detecting as matter that isn't physically present in our universe?
Well, that's an interesting, rather topical question, actually. We don't have a good idea at all what dark matter is. We can only see its gravitational influence on other objects in the universe. If you look at galaxies and you measure how fast those galaxies are rotating and estimate how much mass is in those galaxies, you realise that they should really spin apart because of the centrifugal force. There must be some gravitational glue in there sticking that galaxy together, and that mass isn't producing any light, so we call it dark matter. But we have very little idea what that mass is. We've had some theories, and one of the leading theories up until a few weeks ago was that it was particles that particle physicists call supersymmetric particles. But you may have seen in the news in the last few weeks, the latest news from the Large Hadron Collider is that those supersymmetric particles probably don't exist. So I think we're back to the drawing board, actually, in trying to work out what dark matter actually is.
It's a tough one, isn't it? Because we know it's there, we can see its effects, but we have no idea how to actually start trying to measure it.
That's right. I mean, I think the evidence will come from experiments like the Large Hadron Collider. This is almost certainly some new kind of particle that we don't as yet know about, but which I'm sure we will discover at some point.
Now, we have a special guest with us in the studio this week. She'll be talking to us more in detail in a second because she's actually published a pretty important paper this week. Professor Sharon Peacock is from Cambridge University. She is a microbiologist and she's an expert on how you apply genetics to microbiology. But Sharon, hello. I just wanted to grab you, if I may, since you're here, because Ryan in Norwich just sent in a text message. This one may take you by surprise. He says, "Why do feet smell?" And I immediately thought of you, not for the wrong reason, but because it is all down to microbes, isn't it?
Yes, I understand that. I'm no expert on smelly feet, I have to say, Chris. But the way that you smell is often down to the way that your bacteria are metabolising organic matter that's actually secreted from your body. So, for example, smelly armpits and smelly feet are due to bacteria breaking down components of the body, secretions. And so it is down to that, I'm afraid. And perhaps washing your feet to get rid of the bacteria might be a good...
Why feet specifically, rather than other bits of the body?
Well, that's interesting. I'm not sure I know the answer to that.
Stewing in trainers, lots of
Yes,
sweat.
I think old trainers probably have a lot to do with it. Certainly new trainers don't seem to smell as bad as old trainers. So no expert on smelly trainers, but I think that you could say that it's down to the flora, the bacteria that are on your feet.
Sharon, thank you. So basically, to answer your question, Ryan, it's down to the microbes that are living on you and in between your toes, and they're consuming the dead skin that your surfing out. I think it's something like 40,000 skin cells a minute leave the body. It's 1.5 stones in dead skin over a lifetime that we accumulate in just dead skin that we slough off into the environment. And all of the sweat that we squirt out, I think it's 1.5 litres of sweat a day gets squirted into your socks, and you sort of cook up this lovely bacterial banquet in your shoes. And because the air can't circulate, the bacteria do flourish, and some people have smellier feet than others. Ari's with us. Hello, Ari.
Oh, hello there. I'm curious, is it possible to reset your caffeine tolerance?
Oh, yes. So tell us the background to this, because this is getting hooked on caffeine and that kind of thing. Tell us about your caffeine habit.
Yeah, well, I drink coffee, but nowadays I've been drinking more and more energy drinks. I was just wondering, is there another way to stop building up your tolerance to caffeine other than taking a break from drinking?
Quick question. How do you know that you've developed this tolerance to caffeine? Are you sort of quivering in your seat and things like that? Because I know that if I have one coffee too many, and I know I have, but I get sort of shaky and start talking too quickly.
Yeah, something like that, but also I tend to start to get more drowsy sooner than I think.
So you have to have the caffeine to stay awake, and if you don't have it, then you nod off. I think I know that syndrome.
Something like that, yeah.
Does that happen in your house, Dominic?
Yeah, I mean, you should ask my housemates all on night before I've had my morning coffee.
Jenny, what do you think?
Well, caffeine's used by so many people to keep them feeling awake. It's probably one of the most commonly used drugs, but it actually works by countering a substance in your brain known as adenosine. And this builds up during the course of normal brain activity. And then there are receptors to monitor the amount of this substance. And that's sort of how your brain tells when it's, coming to the end of the day and you should maybe be getting a bit sleepy and thinking about going to bed. Now, caffeine is really clever because it looks quite similar to one of these adenosine molecules, so that it actually fits into the receptors but doesn't activate them. So because the receptors are then blocked by the caffeine molecules, your brain's tricked into thinking there's less adenosine there, and so you don't get the feelings of sleepiness. And that allows your brain's natural stimulants, the dopamine and glutamate molecules, to work freely without being inhibited. The strength of these effects can vary from person to person, and it depends on loads of different factors, but partly it's their level of tolerance. And like with all drugs, continued use of caffeine does build up this tolerance. So the first time you have a cup of coffee, you probably feel its effects very strongly. But if you've been drinking 5 cups a day for 10 years, you probably stop feeling the effects at all and actually just need it to get back to a normal level. You can think of tolerance in a way as the brain trying to get back to what it was like before you started drinking caffeine. So if you push it in one direction, it's going to try and push back in the other direction. But that then means that if you take away the caffeine, your brain's then too far the other way. And this is why you get the withdrawal symptoms, which can be quite extreme. A lot of people...
Headache.
Yeah, a lot of
Really
people get
bad.
headaches, but you can also get nausea, you can get irritability, all sorts of horrible things. This tolerance can build up really quickly, actually, between 1 and 2 weeks, and can be really strong. So even very high doses of caffeine can start not increasing your alertness after only sort of 18 days or so.
There was a chemist in Glasgow University who did a study where he wanted to know how much caffeine was in the coffees being served up at the average coffee house. Because if you go and buy a packet of cigarettes, for example, it'll tell you how much nicotine there is in the cigarettes. If you go and buy an alcoholic drink, it will tell you how much alcohol there is in it. You can go to any coffee chain and buy a coffee, but it doesn't tell you how much caffeine is in there. And this is important because there are risks to health for certain groups. I mean, women who are pregnant, it's been shown, should probably try to keep their caffeine intake down below about 2 cups a day, because any more than that can actually be associated with miscarriage. And this gentleman found, by going into a number, I think more than 20 coffee shops in Glasgow, ordering an espresso and then immediately taking it outside, putting it in methanol and then freezing it in his lab to preserve the caffeine, he found that there was anything between 50 micrograms of caffeine, which is the equivalent of a reasonable strength coffee, up to 300 from one coffee shop. So that's the equivalent, in just the same beverage, of having 6 cups of coffee in one go from one store and just 3 in another. It's amazing, isn't it? It's incredible dosage.
Wow, yeah, that's a huge difference.
So what should Ari do then? Should he ditch the coffee?
Sadly, the only way to get over this tolerance that I've found is to stop drinking the coffee. And now there are people who say it's better to go cold turkey, and you may feel a bit rubbish for 10 days or so, but then it will get better. Other people say it's better to bring it down gradually. I think that's up to you. But the only real way to get over it seems to be to to stop it so that your brain can recover, basically.
I had a friend who said that he played the most awful practical joke on a housemate by swapping his jar of coffee for decaf without telling him, and then the guy couldn't work out why he was in such a bad mood for 2 weeks and had really bad headaches and couldn't get out of bed. Nasty trick. Planet Earth time now, and best known for Brunel's Clifton Suspension Bridge, the Avon Gorge in Bristol in southwest England is also home to several unique species of plants. Some tree species here, varieties of sorbus, aren't found anywhere else in the world, and they've evolved an unusual reproductive process. Planet Earth's Richard Hollingham clambered down a steep path into the wooded gorge to talk to Mandy Levers from the Avon Gorge and Downs Wildlife Project, and also Simon Hiscock, a professor of botany at the University of Bristol. Richard started off by asking Simon how you would spot a sorbus tree.
Its common name is whitebeam because of the colour of the leaves in the spring. They're members of a big family, the rose family, Rosaceae.
So point some out to me. Where is one?
Just up there, there's one of the rare ones that we only find in the gorge, Sorbus bristoliensis, and also over here, Sorbus wilmotiana, which is another endemic to the gorge. And
so they're sort of spindly trees with the leaves.
The leaves
on
are
the
quite
top,
palish up at the top, and they're
small
falling
leaves
at the moment, and they have this sort of white tinge, which is much more pronounced in the spring when they first come out.
So what's special about them? What makes them different?
Well, what's special about the ones in the Avon Gorge is that we've got a process of evolution going on here that is constantly generating new genotypes, new species through processes of hybridization. This is when two distinct either species or microspecies cross-pollinate to make hybrid seed. The hybrids reproduce principally by asexual reproduction, making seeds without sex, and then every so often there's a leaky bit of sex involved, back-crossing to one of the sexuals or to another form, and this then generates hybrids which are then maintained by asexual reproduction. So it's a very sort of fluid process.
So Mandy, in terms of the area here, not just the individual species, how important is this in conservation terms?
Well, the Avon Gorge is considered to be one of the top 3 sites of rare plants in England. There are 27 nationally rare and scarce plants that grow here. So it's internationally important as a special area of conservation, and also nationally as a site of special scientific interest.
I have to say, it doesn't look... It's pleasant. It doesn't look particularly special.
Well, a lot of the plants that grow here have been growing here for a very, very long time, and most of them are very, very small. The white beams are really an exception. So things like the Bristol onion and the Bristol rockcress, which just grow here and nowhere else in the rest of the country, but they all belong to a community of limestone grassland plants, and that's what's particularly important about the Avon Gorge.
What difference has it made having science underlying the work here?
It's always been very traditional for conservationists to just go out and remove bramble and ivy in trees if they're threatening grassland plants. And we've been working with the university really to look at how science can help us make better decisions when we're managing the area.
So the curious finding that we've made is that these new hybrids, which can be different numbers of chromosomes compared to the parents, although they're reproducing asexually, producing seeds without sex, they do need pollination in order to drive and trigger the asexual formation of seeds. So this is quite curious, and we've found that among the rare hybrid species like Sorbus bristoliensis and Sorbus wilmotiana, this is being driven not by their own pollen, but by pollen from another species, particularly Sorbus aurea, the original parent. And so these asexual plants, these rare plants, need to be pollinated by another sorbus in order for them to set their asexual seed. It's very complicated, but the key finding is that Sorbus aurea is important for providing the pollen that triggers the asexual seed set. So we've got to preserve enough Sorbus aurea in the gorge, even though it's very, very common. We've still got to look after it in order to drive the reproductive process of the rare endemics. And further their survival.
So they're all still interlinked, even though they're separate species?
Yes, this is a sort of new idea in conservation and wildlife management with these plants, is that you preserve the process rather than necessarily the rare plants themselves.
Simon Hiscock, a professor of botany at the University of Bristol. You can hear more of that interview from the Planet Earth podcast, which you can find on our website at nakedscientists.com/Planet Earth. Let's find out from Ben how he's getting on with Twitter, with our Round the World Naked Twitter link-up. We're doing a sort of Mexican wave by Twitter. We'll find out how far we've got. So, Ben, we issued your tweet, Cambridge Calling. How are you getting on?
Well, they are coming in faster than I can possibly read them, and I'm getting quite a good geography lesson as well as reading lots of tweets here. But
where have you gone?
Well, let's kick off quite locally. We have Francesca in Norwich, Asher in Cambridge. We have had a tweet from northwest London, getting a little bit further away there. Wentworth in Essex as well. So certainly a good representation of the UK. Paul Howell also in Cambridge. Spreading a little bit further away, Kat Williams has tweeted from Devon, and Jessica from Plymouth. Michelle Rogers in Reading. Mark Hampson's in Bletchley Towers. So certainly the UK is quite well represented. Europe, not quite so good yet, but we are starting to break out into Europe. So we've got one from Bern in Switzerland. We've got one from Rome in Italy. That's Jenny Parkinson. So we're starting to break our way out there, but obviously we need to get a bit further and possibly a bit faster. We've got about 40 minutes left, and we're going to see if we can get all the way around the world. So come on, you Southern Europeans, come on, you Americans, let's see quite how far we can get it.
So they're looking for a tweet coming from @NakedScientists, and if you get one of these tweets that Ben's sending out saying Cambridge Calling with love from Cambridge to the world, please retweet it on and tell all your followers to do the same, and also follow @NakedScientists, and we will retweet that tweet to all of the thousands of people who follow us, and we'll hopefully create this giant Mexican Twitter wave going around the world. You've got one looking at the list here, Ben. Someone's in the bus shelter just by the BBC.
Well, yes, this was the closest one. It's almost a little bit stalkery, but yes, we've had a tweet from someone who said that they actually listen in the bus stop, which is about 100 metres away. I think we can probably see it, and that's from Sylvia Knight. So she's saying she listens very, very locally. I think that's probably the real birth of this Mexican wave.
Thank you, Ben. Dominic.
Now, Chris, we've had a question here from Grace Higgins, who I gather is a Naked Scientist listener in Waterbeach, and she's 11 years old. She wants to know, why do blue biros smell salty?
Well, I don't think they necessarily smell salty, but I know what she means, because if I scribble with my pen on my bit of paper, there is a distinctive smell goes up, isn't there? And biros are actually quite clever. They're really a feat of amazing engineering. What they consist of is a little ball which is in the end of the biro, and that is rolling around freely, and connected to it is that straw-like structure inside the pen which has got ink in it, and the ink has just the right viscosity or thickness so that when the ball rolls round, a thin layer is plastered over the surface of the ball goes round a bit further, transfers or prints that ink onto the page, leaving a line, and then rolls around a bit further and picks up more ink. Now, to get that ink to behave in that way, you've got to have it just the right runniness and then be very quick drying. And they do that using chemicals which are called solvents, and one of them is called polyethylene glycol. It's the same stuff, ethylene glycol, that you put in antifreeze, and it makes things runny, but it evaporates very quickly, and it has quite a strong sweet odour. So there are a number of these solvents, one of them being this antifreeze-like molecule, so I suspect what Grace is smelling is one of these solvents as she writes with her pen. And lots of pens use a similar thing. If you use a felt tip, they haven't got a ball in them, but they've still got ink which has got solvents or things that dissolve the ink in with the ink molecules, and when you draw a line on the page, then the solvent evaporates, leaving behind just the ink molecules stuck into the page surface.
So is it safe to be smelling that solvent?
Well, in the concentration you'll get from a biro, I don't think there's too much risk. It's more dangerous what you write with the pen than what you'll find actually contained in the pen. You're listening to The Naked Scientists, Chris Smith, Dominic Ford and Ginny Smith. If you'd like to get in touch with the programme, we're answering all of your science questions for you this evening. You can email chris@thenakedscientist.com, which is what Joanne Sexton has done, Dominic, and she's wondering, why does my car sat-nav say I'm travelling at a different speed to my car speedometer? Usually the speedometer says I'm going faster than the sat-nav. Which should I believe?
It's partly a safety measure that car speedometers tend to read a little bit on the high side. And that means if there's any slight uncertainty in exactly how accurate that speedometer is, if you're driving along in a 40-mile-an-hour speed limit, balancing your needle on 40 miles an hour, at least you've got a pretty good idea that you're not speeding. You might be doing a bit under 40, but you're not actually breaking the law. There's also some uncertainty because the car doesn't know exactly how big the wheel of the car is. It only knows how fast that wheel is rotating. And if your wheel is slightly bigger, then it's got a bigger circumference to that wheel, and you'll be travelling further for each rotation of
In other
that
words,
wheel.
when you've put new tyres on the car, for example, then the wheel is actually going to go further for each rotation than when the tyres have worn down. And
That's
for that
right.
reason, the speedometer doesn't know whether the tyres are new or old.
Yes, so to err on the safe side, it will assume that you've got the biggest possible tyre that you might have, and maybe even slightly bigger than that by 5 to 10% maybe even. Whereas, of course, the sat-nav system knows exactly where you are on the surface of the Earth. It can work out exactly how fast you're travelling, and so that will tell you exactly the right speed.
Dominic, thanks very much. Les is in over. He's with us. Hello, Les.
Hello. I was wondering, how could the Romans, and predecessors to their great empire, manage to make wine, because of the hygiene seems to be needed to make it these days?
Oh, I see. What an excellent question. So what you're saying is that these days when we try to make beverages, then if we're not careful, they end up contaminated to death.
Yeah.
And yes, you get them spoiled, don't you? Well, the answer is it's the same when they used to make beer, for example. In fact, people used to drink a lot of beer in Roman times. It wasn't the high-strength stuff we have today, because the water was so contaminated that actually the wine and the beer were better to drink because they were less likely to be contaminated because they had alcohol in them. Basically, if you take grapes and you just pick them off the vine and you have relatively good, clean starting water, what you're actually relying on is not having sterility in the system, because the yeast all comes from the grapes in the first place. If you've ever picked fruit, you may have noticed this, Les, if you look at the surface of the fruit, unless you buy it from a supermarket, if you go and get fruit off the tree, what does the surface of a picked plum or some grapes look like if you look at them?
Oh, it's got a little bloom to it usually, and almost a coating in effect, I suppose you could say.
That's right, and if you were to take some of that coating and put it under a microscope, what you would see is that that's mainly yeasts. So there are microorganisms there, but there are lots of yeasts there naturally on the fruit. And if you put those into ideal conditions so the yeast can start to grow, and what the yeast is going to be doing is to consume the sugars in the fruit, and it's going to, if you do it without oxygen being there, it's going to convert the sugar into alcohol and some carbon dioxide. Because there's so much yeast there, pretty quickly it will outcompete the other things that shouldn't be there, and it will suppress their growth because the alcohol is toxic to the other organisms. The yeast can tolerate it, though, and so the yeast outgrows it. You end up fermenting the wine, and you make a high alcohol or relatively high alcohol beverage where you've used the alcohol actually to suppress the harmful microorganisms, so it's sort of self-sterilising.
Okay, thank you.
Ginny, Paul wants to know, why do we usually sneeze more than once at a time? Do you have sneezing fits? Or is it just singles for you?
No, I tend to only ever sneeze once, but my boyfriend always sneezes 3 or 4 times every time he sneezes. So it's quite interesting. Different people do seem to sneeze differently. Well, sneezing is a reflex that occurs in response to a stimulus, some kind of irritant, something annoying entering the nose. It's semi-autonomous, which means that although it is a reflex, we do have some control over it. So you can sometimes manage to stifle a sneeze, but it can be quite tricky to do that. So it can be a normal irritant like dust, pet hair, some kind of virus or microorganism. But in many people, including me actually, sneezing can also be triggered by bright lights. So if you go out into the sunshine...
Photic sneeze reflex. Yeah,
exactly.
We've talked about that before.
Okay. So yeah, these sneezes are triggered when a particle of some kind makes contact with your mucous membrane. And then that sends a response to your brain, a signal to your brain, and the response is this very dramatic sneeze, which actually uses a whole load of different muscles, because you need some muscles to actually sort of brace yourself against it. Otherwise, you go careering across the room when it happened. It doesn't really seem to be understood why different people sneeze differently. There may be a genetic component, there usually is to these things. I found one thing that said that it may be more common in allergenic individuals, so people who are responding to chronic irritants that are sort of there all the time. So if you've got hay fever or if you've got pet allergies, you may be more likely to sneeze lots of times in a row.
Dominic, quick single or huge, great, multiple guffaws?
I think unless I've got a cold, I tend to go for a quick single, but when I've got a cold, I just can't stop.
Someone asked me the other day, do you sneeze in your sleep? And I had to think about that. I don't think I ever have. But then you wouldn't know, I guess.
You'd know.
Do you know?
I don't think I'd sneeze in my sleep, but I'm not sure I would know.
Let's ask the audience. So, if you can tell us, can put us out of our misery, is it possible to sneeze in your sleep? Because I really don't know. I would think it is, because it's a sort of airway clearing reflex, isn't it? Email chris@thenakedscientist.com or tweet @nakedscientist. And talking of Twitter, Ben is marshalling thousands of tweets now, I think, on how we're getting on with our round-the-world tweet Mexican wave. What have you got to? What's going on?
Well, I'm not sure if marshalling is the right word. I think perhaps drowning in might be more appropriate. But we're getting lots of calls in here from people asking questions. But on Twitter, we've definitely broken the equator, so we are getting lots of tweets from various parts of South Africa. And I'm really pleased to say, halfway through the show, we've already made it down to Adelaide and Perth and various bits of Australia. So,
wow, who have we got in Perth and Adelaide then?
Well, we've got a number of people, actually, almost too many to count, to be honest. Dr. Paul Willis is there. He also pointed out, of course, that we were talking earlier about the effect of staying up late at night working on computers, and yet here we are causing people to stay up late at night looking at their computers.
In Adelaide, what's that, 4 o'clock in the morning, is it?
Oh, it must be something like that. Again, this geography lesson is going over my head at the moment. But we're still getting people from very local regions as well, North London, Peterborough. We're getting lots and lots of things. And this, of course, proves that you don't have to rely on the speed of a communication to travel when you're on the internet, because it is actually a network. We're getting people in Australia at the same time as people in London and the same time as people in Scotland. Lots of people from Canada. I'm really pleased to say that we've got tweets from Tucson, Arizona. They're coming in from everywhere now, but do keep them coming, and I will try my best to keep up with them, retweet everything, and we will try and archive all of these so that you can eventually see who you were tweeting at the same time with and see all of the people that you managed to reach out to at the same time as us here in Cambridge.
It is amazing the power of the sort of social network now, isn't it? I mean, I know that we're doing this as a sort of a gimmick, but it is demonstrating actually how quickly information these days can travel. If you think about it, 100 years ago, to get information to Australia and back would have been maybe a year. Well, now let's change direction very slightly, because this week the journal The Lancet Infectious Diseases ran a rather unusual detective story. But this is one where rapid DNA sequencing was actually used in a hospital to track down an outbreak of MRSA, methicillin-resistant Staphylococcus aureus, and they found an unsuspecting carrier. Now, it bears all the hallmarks of a very good television docudrama, but actually this took place really here in Cambridge, and the research paper that the researchers have published is said to be the first example of actually using this technique to bring an infection to a close. And the author of that study is Professor Sharon Peacock from Cambridge University. She's with us. Hello, Sharon.
Hello, good evening.
Why did you do this?
We want to control MRSA transmission, passing it from one patient to another as much as possible, because we want to contain any infections that might arise. And so we need to see when MRSA does move from one person to another, and we need to see it fast. Now, the way we do that at the moment is we work out whether two patients who are MRSA positive could have got it from each other because they're in the same ward at the same time. But what we can't do at the moment is to do any sort of typing on the bacteria to see how related the two are. Now, if we had a tool where we could see that they were either related or unrelated, that would be very helpful, because we could work out if transmission had occurred from patient A to patient B. But those tests aren't available at the moment, and that's a problem for us.
So we know that the two patients have got MRSA, but there's more than one form of MRSA at a molecular level. So we don't know whether they've come into the hospital independently with their infection, or something in the hospital is transmitting these infections between these individuals.
That's exactly right. You can't see the transmission pathways between patients. So what this new technology does is to actually sequence the whole genome of the bacterium. Now, even just a few years ago, sequencing a bacterial genome would have cost hundreds of thousands of pounds and taken several years to do a single one. There's new technology now available which allows you to do sequencing of multiple genomes within a day, actually, very, very fast. And the price is actually falling very rapidly. That means that we can bring this technology to clinical practice quite soon. And so in this study, this research study, we really wanted to test out how useful that could actually be in trying to understand better an MRSA outbreak on our special care baby unit at Addenbrooke's Hospital.
Can you talk us through how you actually did the study? What were the steps, and how did you investigate what was going on?
Well, we had access to this technology, and we knew that there was a suspected outbreak of MRSA on our special care baby unit, which had been investigated by our infection control team. Now, they were not sure whether an outbreak had occurred over an extended period of 6 months. There were cases coming into special care who were MRSA positive, but they weren't sure if they were all linked. And the reason for that is because throughout that 6 months there were quite large gaps when there were no people who were MRSA positive at all. And so one has to ask, how has that transmission gap been closed? So what we did in the first instance was we took all of those isolates and we sequenced them, and we were able to say very quickly that they were all so related at the genome level that this had to be an outbreak. So at the same time, we extended our search to look for bacteria that are coming from GPs, actually, in outpatient departments. We sequenced those, and we found that actually the outbreak was twice as big as we originally thought, and that there were cases actually in the community. People had developed infections, and we really only linked that to the special care baby unit through the sequencing.
So that meant that you were then able to say, right, there are outbreaks occurring. How did you then go and find the individual that was causing those outbreaks?
Well, having identified that there was definitely an outbreak, we put the special care baby unit under very close surveillance to see if new carriers or people infected with MRSA popped up. And actually 2 months after the previous MRSA carrier, we found a new MRSA carrier, an infant. And we were puzzled by this because there was obviously a very long gap when we saw no MRSA at all. And it was at this point that we thought there must be a carrier amongst a member of staff. And so we gathered the staff together and got full agreement that they would be swabbed. And we swabbed 154 staff members and found just one that was a carrier. So, of course, we immediately sequenced that, and it was a direct match to the outbreak strain. And so what we think is that this person was involved in the outbreak. What that allowed us to do was to actually treat that individual so that the MRSA carriage was removed from them, and that effectively stopped the outbreak from continuing any further.
How do you know that they gave it to the kids and not the other way around?
I think that it would be difficult to be absolutely unequivocal about that individual causing spread throughout the entire outbreak. But what we did do with the staff carrier was we sequenced lots of single bacteria from their carriage population, and we got genetic matches to before the 2-month gap and after the 2-month gap. So we think that that is fairly strong evidence, actually, that that person was at least involved in that transmission event.
This is obviously extremely helpful in terms of guiding infection control strategies, but are there any other uses for this sort of technology in guiding how we tackle bugs of all kinds in hospital?
I think actually that there will be numerous applications for this. We'll need to work out exactly where, when and how to use it. But for example, it could be really key in investigating foodborne outbreaks to work out if there is an outbreak and to help contain that. We could use it, for example, to get rapid drug susceptibility testing for people with tuberculosis. So there's a very wide range of applications for this technology, and I think that we'll be seeing these brought into use in the next few years.
Sharon, thank you very much. That's Professor Sharon Peacock from Cambridge University. Dominic, lovely question here from Bruce Robertson on email, chris@nakerscientist.com, and he says, when flying, say, from Europe to South Africa, it's about a 10 to 12 hour flight, and when starting the flight, the destination airport will be in a different place to when you arrive, in other words, because the Earth is turning. So how do they get round that?
Yeah, I mean, that's a fascinating idea, isn't it? I always like the idea that perhaps you could take off in a helicopter in London and just float in the air for 6 hours or so and then descend and land in New York, and that would be a very cheap and easy way to cross the Atlantic. In fact, any aircraft is travelling through the Earth's atmosphere, and the Earth's atmosphere is moving with the rotation of the Earth. So, unfortunately, the air that the aeroplane is travelling through is also rotating, and so you don't have to take any special account for the fact that the Earth is rotating because you're being carried with that medium. And obviously the reason why that is because there's friction between the air in the atmosphere and the ground below, and that friction will start the air rotating with the Earth. And at the top of the atmosphere there's no friction there with space because there's nothing above the atmosphere. So with time the atmosphere just picks up the Earth's rotation.
You've sort of also answered the True Hopes email question, who wanted to know why does the atmosphere move along with the Earth's rotation, and you've answered that in that question as well. Thank you, Dominic. Ginny, one for you. This is from Rodney Edgecombe, who says, do high testosterone males have more female offspring?
Okay, well, we all know that the sex of a baby is determined by whether the egg, which is carrying an X chromosome, is fertilised by a sperm carrying another X, which would produce a girl, or one carrying a Y chromosome, which produces a boy. So in that sense, it's the sperm that decides the sex of the baby. But what determines which sperm is the first to reach and fertilise that egg, or which sperm are even in the mix, is a lot more subtle and less well understood.
Because the ones that are Y-bearing, that are going to give a boy, because the Y chromosome is slightly smaller than the X, some people have argued that they are less of a weight burden for the sperm to push along when it swims, and therefore the Y ones move a bit faster than the X ones. So depending upon how you time the exposure, let's say, you could have a boy or a girl.
And there is actually, I think it's a 51 to 50 to 49 ratio boys to girls, which fits with that idea that the Y chromosome sperm is slightly faster. But there are other things that can skew that. So actually, it's the other way round to the question. So studies seem to show that men with lower levels of testosterone are more likely to produce female offspring, and those with high levels are more likely to produce male offspring. So, for example, they found that men with prostate cancer, which is very strongly linked with high testosterone levels, tend to have more male than female children. On the other hand, men who have fertility problems due to lower testosterone tend to produce females when they do father a child. There was even a study conducted at the University of Glasgow that showed that males who ran further than 30 miles a week at the time of conception are much more likely to produce females.
Do you mean as in when they were themselves conceived, so their mother was running 30 miles a week, or they were doing the running when they were also trying to do the running, conceiving?
I think not actually at the same time, because that would be quite logistically difficult.
I just wanted to clarify that.
No, if you do a lot of exercise, that tends to temporarily deplete testosterone levels. So if conception happens relatively soon after the run, then they tend to be more likely to produce females, whereas people who are doing just a little bit of running didn't show that difference at all.
So the bottom line is?
Low testosterone levels in a male and you're more likely to have girls, but it's a very slim difference. It's only when you look at hundreds of men, it's proportionally. I don't actually think that, going out for a jog beforehand will make you more likely to have a girl.
Jenny, thank you. Dominic, what have you flushed out for us this week?
Well, this is a paper which I spotted in the journal Astronomy and Astrophysics by Felipe Delorme of the University of Grenoble, and he's made the first detection of a planet which is not orbiting another star, but is in fact free-floating in space.
Where did it come from then?
So what we think has happened is that this planet will have formed in a planetary system around a star, but then some physical process has kicked it out of that planetary system. So it's now a loner drifting in space.
Well, obviously the question is, how did they see it? But we can come to that in a second. First of all, how did it get into the middle of nowhere in space?
Well, this is an interesting development because a lot of theoretical models actually predict that planets are quite often kicked out of planetary systems. If you look at computational simulations of how planetary systems form, what often happens is that you form quite a lot of planets. Some of those actually get kicked out by gravitational interactions with the other planets in the system, while the other planets move inwards towards their sun as a result of the balance of energy between the planets which are left and those which pick up velocity and are slung out of the planetary system.
So if we were to take our own solar system as an example, say you were a massive planet like Jupiter a long way out and you moved in towards the sun a bit, then because you are effectively losing some gravitational potential energy as you're going in that way, you're going to accelerate other planets in the solar system, and you're saying potentially to the extent that they could get accelerated so much they will be flung out altogether and they'll just exit the solar system and go off into interstellar space.
That's exactly right. And if we look at a lot of the planetary systems that have been found around other stars, these are exoplanets, you find that often you have planets rather like Jupiter orbiting incredibly close into their parent stars, going round every few days, so closer even than Mercury is to our own sun.
And they couldn't have formed in that position. That's the key thing, isn't it?
They couldn't have formed there simply because there's not enough material there. There wouldn't have been enough material there in the protoplanetary disk. So they must have formed further out, and something must have triggered them to migrate inwards towards their parent star. So we think there was probably another planet that would have been kicked out into deep space.
So that having been the case, or that's the theory, how did they detect this lone planet wandering around in the middle of nowhere? Because it's not a star, so it doesn't produce light that we can see, and it's not a planet close to a star, so it can't bask in a star's reflective glory, for want of a better phrase. How did they see it?
That's a real problem. What they did was to think, if we're going to see one of these things at all, it's got to be a planet that was relatively recently kicked out of its planetary system. So it's still got some warmth to it, which means it will produce some thermal infrared radiation. And then with an infrared telescope, you can potentially try and pick up that thermal infrared radiation. So what they did was to look for clusters of stars close to our own sun. They'd have to be nearby, so you can see this very faint radiation. And then to look just in the vicinity of those and see if you can see any unexplained infrared sources.
Is this a relatively juvenile planet? What I mean by that is, in order to get something which is sufficiently warm still to be giving out infrared in the way you say so we can see it, does it have to be quite newly formed?
That's right. The planet will probably be kicked out in the early history of that planetary system, and then it will get cold quite quickly once it's kicked out, so you want to catch it when it's still young. So this planet, they think, is somewhere between 10 and 100 million years old, which is comparatively young. I mean, our solar system is 5 billion years old, so this is a young system. It's at a distance of about 50 light years in the constellation of Doradus in the southern hemisphere, and this is just a cluster of young stars where there's this one planet that appears to have been kicked out.
Is this a relatively rare, or do you think we're going to see many such examples of this now we're getting better at finding them?
Well, this has been a problem for a theory up until now, because theories have predicted these objects must be there, but without actually seeing them, it's difficult to constrain which of those theories is correct. Now, most of those theories do predict there's quite a lot of these planets, but what's crucial is how many. Now, one doesn't tell us how many there are, but if we can start to get hundreds of these things, then that can really tie down which of those theories is correct. And this is a proof of principle, that the state-of-the-art telescopes can detect these cold planets. And over the next 5 to 10 years, I think it's quite likely we will start to see these being detected by the dozen, and that will be really interesting.
You are listening to The Naked Scientists. Chris Smith, Dominic Ford and Ginny Smith here answering your science questions. This one just in for you, Ginny.
Hello, I'm Rin from Estonia, and I love listening to your podcast every time when I'm walking here in my university town Tartu. I was wondering what happens to human body when something or somebody scares it. I tend to be frightened easily, and because of that, I also wanted to know how badly it really affects me.
When something scares us, a signal is sent to our amygdala, which is a part of the brain that controls emotion. So the first signal that's sent actually bypasses the conscious part of your brain. And that explains why if you glance at a piece of rope out of the corner of your eye, you get scared before you consciously see it and realise that it's not actually a snake, it is just a piece of rope. But that fear comes before that realisation. And the second response, because it's slower, it travels through the cortex, and that gives you the conscious control and the realisation of, oh, it's just a piece of rope, it's not going to hurt me. Now, if it had been a snake you'd seen, the feeling of fear would have also been accompanied by what's known as the fight or flight response, and that prepares you to respond to danger. Your sympathetic nervous system becomes activated, and this releases adrenaline into the bloodstream. Your pupils dilate, allowing more light into your eyes, your heart rate and your breathing increase, sweat's produced and digestion stops. Cortisol, which is known as the stress hormone, is also released, and this increases glucose levels in your blood to provide extra energy. And all of these things are to prepare you to either run away from the source of the fear or to attack it, to fight back. Now, in modern life, those two options aren't always possible. If the source of your fear is a big presentation at work or something like that, then running away or fighting it aren't really possible options.
You won't get the promotion.
No, exactly. So in this case, these mechanisms which evolved to protect us may actually be detrimental to our health. Prolonged stress responses, so if you stay at this heightened level of arousal, of fight or flight for a long time, it can actually weaken your immune system and increase your blood pressure. So it can make you more susceptible for colds and flus and that sort of stuff, and also increase your risk of heart attacks. So, yeah, if you do have a very stressful job or life, or you get scared a lot, it's probably a good idea to try and take a break every now and again, let your body calm down a bit and recover.
What happens if you've got to go on the radio, do a radio interview?
Well, I mean, short levels of this stress is actually quite beneficial. So
it doesn't feel beneficial sometimes.
It can actually make you perform better. A lot of performers find that if they don't get a bit of nerves before they go on stage, their performance suffers. There's this inverted U-shaped curve, so there's a beneficial level, and then if it goes above that, it starts being detrimental again.
I think I'm in the detrimental phase, if I'm honest.
So short bursts of it can be good, but what you don't want is to stay at a very high level of adrenaline release for a very long period of time.
Ginny, thank you. Remember, we're doing our Round the World tweet. We're trying to get to as many countries as we possibly can over the hour of the Naked Scientist programme. We're trying to demonstrate that the world is not the tiny place it once was, and that in fact the power of new media and social media carries messages worldwide very quickly. Ben Valsler is in our control room trying to marshal all these tweets. Who have you got tweets from now, Ben? Where have we got to?
Well, it's still going all the way around the world. We have Redski in Qatar, who has tweeted. He actually said, now it's bedtime, which I think is fair enough, and thank you for staying up. We have a tweet from Erin in Idaho, Steve Carter, quite local, Welling Garland City, Bruce McAllister, not local, East Rand in South Africa, going all the way around the world. Anna Berg in Durham in North Carolina, so not our Durham, but the Americans' Durham. David Stoll in Hansted, Greyface from Cork in Ireland, and Robert Blythe in Saskatchewan in Canada, and my favourite so far is from Shashama in Kathmandu in Nepal.
Fantastic. Have we got anybody? I saw Siberia pop up earlier. You may have missed that one, go past.
I will hopefully catch up with all of them, but certainly we've got Belgium, that's Jürgen, we've got Luke in Valencia, Amy in Minneapolis, David in Windsor in Canada, and someone called Without a Diagnosis in Paynton.
Thank you, Ben. So you have about 9 minutes left to follow our Naked Scientist Mexican Wave on Twitter. You have to follow @NakedScientist, and when you see our tweet come through, retweet it onto your followers, telling them to do the same, but also tweet back to us @NakedScientist, telling us where you are and any message you want to. Someone tweeted us from Chile, Birmingham earlier. Yeah, it's chilly here too. Dominic, is the gas in gas giants highly compressed? Orlando says, I was wondering if planets like Jupiter are just gas. Why is it that they exert such enormous gravitational pull on surrounding matter, like the asteroid belt?
Well, planets like Jupiter certainly do have cores. Jupiter, we think, has a rocky core which is about 10 times more massive than the Earth. But Jupiter itself is a really vast planet. It's got 300 times the mass of the Earth, and it measured about 10 times the radius of the Earth across. And most of that volume and most of that mass is a mixture of hydrogen and helium gas. And that gas is very heavily compressed, and that's how Jupiter manages to be so very massive. In fact, it's in a state of hydrogen called metallic hydrogen, where these molecules are so compressed together that they form a lattice, and the electrons, rather than orbiting around individual hydrogen nuclei, actually can flow freely through that metallic hydrogen. And that's why Jupiter has such a strong magnetic field, because it's electrons flowing through that metallic hydrogen which is producing that magnetic field.
How did it get all that gas in the first place? Hydrogen and helium being so light, how did they manage to coalesce around Jupiter before it got big and had lots of gravity?
Well, that's an interesting question that people are actually still researching, but I think the best theory at the moment is that when a planet gets to a mass of 10 times that of the Earth, its gravitational field is then so strong that it can pull in gas around it, and you have this sudden catastrophic fall of material onto this planet. And so any planet of less than 10 times the mass of the Earth will tend to be rocky, like the inner planets of the solar system, and any planets that creep over that mass suddenly turn into these vast gas giants like Jupiter and Saturn.
Thank you very much, Dominic. Now, from one hard question to another, Hannah Critchlow is in sync for this week's Naked Scientist Question of the Week.
The Naked Scientist's Question of the Week, brought to you in association with the How to Wisman Foundation, supporting science and education from Alpha to Omega.
This week, we go in search of synchrony.
Hi, this is Michelle from Dixon, New Mexico. I would like to know if there is a scientific or evolutionary reason for women's menstrual cycles to sync when living together.
So, does menstrual synchrony actually happen? And if so, why? We turn to evolutionary anthropologist Dr. Jo Setchell at Durham University.
Menstrual synchrony is a really fascinating topic. If you talk to almost any woman, she'll tell you that she's experienced it at some stage when she was living closely together with other women. They started to have their menstrual period at the same time. But it's actually also a very controversial topic in terms of science. So although there are some very well-known studies that claim to show statistically that this phenomenon happens in humans and also in laboratory rats, and in fact there are even some studies that claim that synchrony is caused by pheromones, all of those studies have been strongly criticized for the methods that they used. And in fact, sadly, if you use correct statistical methods that control for all the confounding variables, then you actually find there's no evidence at all for synchrony. So an example, the mandrills that I've been studying for years now. So these are a large forest-dwelling monkey, and we're very fortunate that female mandrills have big swellings around their fertile period, so you can track their menstrual cycle very easily, much more easily than you can with humans because we hide ours. And when we actually looked at these animals to see whether the female cycles are more synchronous than you would expect from pure chance, then we found that they're not different at all. So basically, even though when I look at the data on the computer screen, I think you can see patterns of synchrony, actually the statistical models are telling me more about my own perception of the patterns than they actually are about the data. So although this is a very appealing idea and we all think we've experienced it, I think cycle synchrony actually tells us more about our evolved ability to detect patterns when there aren't any. So we're much more actually likely to notice incidents when we cycle at the same time as a friend than we are to notice when we don't. So you can actually think of this like lying on your back in the park and spotting faces in the clouds. So the really interesting question is why we spot patterns, and the reason for that is probably because it's much better for us evolutionarily in terms of our survival to spot a predator that isn't there than not to spot one that is.
That was Jo Setchell debunking the myth that menstrual cycles synchronise and offering up an evolutionary explanation for why humans identify patterns when they don't actually exist. We next point our questioning ears up to the sky to answer a question just in.
Hi, Naked Scientists. Jodie from Plymouth here. I have a question about Mars. If Mars has much less dense atmosphere than that of Earth, does that mean that sound waves travel slower on that planet than it does our own? Thanks.
So would the sound of a scream take longer to travel through the atmosphere on Mars than on Earth? Send us your thoughts. You can tweet at Naked Scientists, write on our Facebook page, email chris@thenakedscientists.com, or join in the debate on our forum, which is at nakedscientists.com/forum.
Hannah Critchlow, and in the time we have left, let's rejoin Ben to find out if, in the space of this 1 hour programme, we have managed to tweet our way around the world. Ben, what have you got for us?
Well, having a look, I think we've hit most countries. I've just seen the tweet from VJ in India, Ari in Helsinki, Rick Rolling in Wellington in New Zealand, so they really must be staying up late, as well as the more local ones, Mark Looney in Cardiff, M. Kelly in York, Marion in the Netherlands, and Julia, who listens in Snowdonia on her way to Bangor University.
Did we get to Japan?
Now, we did get to Japan just before the show started. Now, I don't know if we can officially count that in our Mexican wave, because they did say they have to be up for work early, so they were going to have to go to bed. But we've certainly got people in Japan who were on the crest, but not quite properly on the Twitter Mexican wave.
They are in spirit, but not necessarily in person at this time, owing to the time difference. There was one I spotted from Neil in Malaysia, and he said he had to go to bed, but he did say he would sleep naked. So he was there in spirit.
There have been a couple of tweets from Malaysia, Kuala Lumpur, Indonesia, Jakarta. So I think we've hit a very significant proportion of the world, which really does go to show the power of modern communications.
Ben Valstar, thank you very much. And we will keep all of those tweets, and we'll try and get somebody to put us together a map or a model of how this actually unfolded, this Twitter Mexican wave. Thank you very much to everybody who took part. What a wonderful experiment. And just goes to show how small the world now is. Well, that's it for this week. Thank you for joining in with the programme, and thank you to Sharon Peacock for joining us to explain about her research on tracing superbugs around hospitals. Next week, we'll be investigating ISIS. This is the STFC's neutron source in Oxfordshire. We'll find out how neutrons can help us to probe the properties of matter and also watch biological interactions at unprecedented resolution. Send in your questions for that to chris@thenakedscientist.com. You can tweet at Naked Scientists or post them on our Facebook page. That's facebook.com/thenakedscientists. Thank you to Ben Valsler and Tom Simpkins for producing this week's programme. And until next time, goodbye.
The Naked Scientists podcast comes to you from Cambridge University and is supported by the Wellcome Trust, the EPSRC, the STFC, the Natural Environment Research Council and UK FAST. For more cutting-edge science, join us online at nakedscientists.com.